Let's get on with it then. So last several times have been talking about Euler circuits and Euler paths. Today I want to talk about something completely different. Actually, it seems like it's going to be quite similar, but it turns out to be completely different. Remember, an Euler circuit is one which uses every edge once and doesn't repeat any edges. And an Euler path is a path which uses every edge but doesn't repeat any. What I want to talk about next is the same thing, but for a circuit which uses every vertex without repeating any, or a path which uses every vertex without repeating any. These are called Hamilton circuits. Hamilton circuits. This is a circuit which uses every vertex once without repeating. That's called a Hamilton circuit. This is not named after the famous American politician and rapper, but there's a mathematician, Hamilton, from Dublin, who this is named after. That Hamilton, Sir William Rowan Hamilton. Actually, Alexander Hamilton did invent some mathematical concepts which are named after him, but this is not Alexander Hamilton. This is the other Hamilton. This is the more famous Hamilton in terms of mathematics. Anyway, a Hamilton circuit is a circuit which uses every vertex once without repeating. Euler circuit is for edges. Hamilton circuit is for vertices. Otherwise, it's the same concept. But as you will quickly see, the way of dealing with Hamilton circuits is totally different from the way of dealing with Euler circuits. The methods that you use are completely different. Even though they seem like superficially similar ideas, they are actually not very similar at all. Let's just do some very simple examples. How about a graph like this? Let's say this graph with an extra little bendy one. Is there or is there not a Hamilton circuit? You want a circuit which uses every vertex once without repeating any vertices? I don't care about the edges. You can miss edges if you want. You just have to hit every vertex. Anybody, I know we haven't talked about any real techniques yet, but anybody looking at this, can you see a Hamilton circuit? You want a circuit which uses every vertex without repeating any. Can anyone describe where it would go? Do you have an idea? Yeah. Sorry, it looked like you had an idea.
I think I do.
I don't mean to call you out. Where would you go?
I would start at the top,
yeah.
Go around the loop, and then just continue across to the middle. Eventually, go down, middle, and then make a triangle. Oh wait, no, that would be a path.
Yeah, it's got to be a circuit, and you got to hit every vertex. Anybody see how you can do it? It does not matter if you miss some edges. You can miss edges if you want. You just have to hit all the vertices. There are 4 vertices that you got to get. What do you think?
Just like a zigzag. So start from the top and then just go.
The old Harry Potter style. I think this is not a circuit. It's supposed to be a circuit. Yeah.
Just go around the diamond because you don't need to go through the edges.
Yeah, let's just go around the outer edge. Around the diamond, she said, right? It doesn't matter if you use all the edges or not. You just have to hit all the vertices. So I'm going to draw this. In the past with Euler circuits, I've been drawing like little arrows. This time, for reasons you'll see, I'm going to just scribble them in. This will make it easier if you don't have colors. You don't really need colors to make it clear. I'm just scribbling. You can scribble the same color and it'll be fine. All right? That is a Hamilton circuit. With Euler circuits, you have to be more careful about drawing the arrow because it's confusing in an Euler circuit, which will revisit every vertex perhaps several times. But a Hamilton circuit never revisits a vertex, so it turns out when you're drawing pictures of them, it's always just very clear to draw your picture. You don't have to be too picky about exactly where the line goes. It's easy to tell exactly where the line goes. All right, that's a Hamilton circuit. So this one has a Hamilton circuit. By the way, can I make a comment about the test, the previous test that we did? There were several questions in there about Euler circuits. Does it have an Euler circuit? Some people said, I just wanted to point out a little sort of socially awkward thing that people wrote on the test. I didn't take out points for this, but some people said something like, this graph is an Euler circuit. You should say this graph has an Euler circuit. So this one right here, it has a Hamilton circuit. We don't say it is a Hamilton circuit. I mean, I know what you mean if you say that, but people will look funny at you at the club when you say it that way. Yes?
So is the Hamilton circuit pretty much denoted by the red squiggly line?
The squiggly, yeah, right.
Okay.
That's the Hamilton circuit. It goes, I mean, it's not really clear on the squiggly where it starts and stops, but that also doesn't really matter because it's a circuit. So it just hits each vertex.
So it doesn't include the other two lines with the one going between the diamond and the other one on the
Yeah,
side.
right.
It doesn't include that.
It misses that edge and that edge, yeah. But a Hamilton circuit doesn't have to hit all the edges.
Okay.
And in fact, it usually doesn't. Because if you hit all the edges, usually that means you have to revisit some vertex, which is not allowed for a Hamilton circuit. That's the point. It hits every vertex once and it misses. In general, it will miss some edges. All right, this one has a Hamilton circuit. How about, let's just try another one here. How about this? We're just doing easy ones for now. We will eventually talk about some real sort of techniques for doing this, but for now, can we just look at it? Anybody have an idea? Do you see, can you do a Hamilton circuit here? There are 9 vertices, right? You just have to hit every vertex. I don't care if you leave out some edges. In fact, you're going to have to leave out a bunch of edges if you're going to do it at all. Anybody see a way to do this? You might think, can I just go around the outside edge again? You can't quite do that because you'll miss the one in the middle, but any idea? Yeah?
So you go down to the right, then the middle vertex, you go inside, then through the diagonal line and back to the first one.
Mm-hmm. So I think you started up here, right?
Mm-hmm.
In the upper left. Yeah. She said go down to the right, up a little bit, then cut into the middle, because you got to hit that one in the middle. Come back out the diagonal and across. Right? Looks good to me. That is a Hamilton circuit. I mean, the red thing that I drew there, the squiggles, that was a Hamilton circuit. So this one also has a Hamilton circuit. All right? I will point out that really when you talk about Euler circuits, everything is about the degrees, right? But the Hamilton circuit, the degrees are far less important. Some things in here have even degrees, some have odd degree. It just doesn't matter. Hamilton circuit is really a completely different kind of thing, and the tricks for finding Euler circuits are totally irrelevant when it comes to finding Hamilton circuits. How about this? What if it was the same thing, but without that diagonal? Can you do it this time? It turns out actually there is no Hamilton circuit here. Now you might think, well, you could try the same thing, go around the outside, but if you come into the middle, you're going to miss that edge in the corner, or if you just go all the way around the outside, you'll miss the one in the middle. I'm going to say this has no Hamilton circuit. No Hamilton circuit. But can I just say it's hard to say exactly why, right? Like if this was a homework problem and I said, tell me if it either find me a Hamilton circuit or say why there is none. It turns out in this example there is none, but it's not so clear. Like there isn't just a very simple thing you can say about, no, it definitely doesn't have one because of this and this and this. Actually, that is what we're going to talk about today. How could you, for sure, convince somebody that there is no Hamilton circuit here, rather than just saying something like, well, if you try to do it, you just can't do it, which is, I mean, that's true, but it's a little unsatisfying from a mathematical point of view. All right, so that one actually I want to come back to once we learn a little bit of techniques here. Here's one actually that kind of an interesting example where you sort of can explain simply why there is no Hamilton circuit here. I'm going to draw, I got 4 dots on the left and 2 on the right, and I'm going to connect them up. Every vertex on the left is going to connect with every vertex on the right. Looks like this. Every vertex on the left connects with every vertex on the right, like so. All right. There's actually a name for this. This is called a bipartite graph because the vertices naturally fall into 2 categories. There's the ones on the left and the ones on the right. Bipartite. There's 2 parts to this graph. And then you have edges connecting all of them. All right. Graphs like this, the typical, like if you look at an old math textbook which has graph theory in it, these graphs are often referenced in terms of like dating relationships or marriages. According to the cis hets, you have like you think of like all these are all the men and these are all the women, and the only ways they can pair up is one with another. That's the cis het version of dating. Real dating in the real life is a little more complicated than that. But anyway, people have used this kind of thing. There are actually real life situations in which things can be categorized into 2 groups where one from one group has to be matched with one from the other group. Anyway, I'm just bringing this up because this here has no Hamilton circuit. And it's a little easier to say why in this example. Think about what if we had a Hamilton circuit, say start in the upper left corner. What the circuit has to do when I go edge to edge, it has to go across every time, right? So starting up there, the next way that the circuit goes, it either has to go to this top vertex or to this one. In any case, it has to like go across each time. Each edge that I add on has to go from one side to the other. And so, maybe it goes over to that top one first, and then it goes back to the left, maybe to this one. I'm sort of making this up as I go, but this whole picture is symmetric anyway, so if you choose a slightly different one than I did, it's not going to matter. Anyway, next you have to go back across to here, and then you have to go back across to one of these that I didn't use yet. And now you're stuck, actually, because once you go back and forth, you can only go back and forth so many times before you've used up all the ones on the right. All right? Really, this becomes impossible in this picture because there's too many on the left and not enough on the right. If they were equal numbers, then you really could go back and forth and cover them all. But since there's an extra ones on the left and not enough on the right, you can't do it. So this has no Hamilton circuit because the left and the right side have different amounts of vertices. And since you have to go back and forth each time, you're going to run out of vertices on the right before you're able to actually cover everything. All right? So this one has no Hamilton circuit. That one you can actually explain why. This is the idea. I'm trying to give you a sense for, these have all been fairly simple examples, but I hope you agree with me by now that really the whole trick or the whole game of Hamilton circuits is quite different from Euler circuits, which is what we've been talking about all along. All right. I would like to discuss how can you actually find a Hamilton circuit. If I show you a graph, this will be like a typical homework problem or quiz question. I show you a graph, you find me a Hamilton circuit, or explain to me why there can be no Hamilton circuit. I would like to, I'm just going to redraw one of those examples again. Our technique is based on 2 very simple observations about a Hamilton circuit. I'm going to draw in the Hamilton circuit here again. All right, that was one of those examples up here. 2 simple properties for Hamilton circuits. All right, I got 2 of them. The first one is about, they're both very obvious things that might not even think of to remark about because they are so obvious. But the Hamilton circuit has to hit every vertex, And what that means is every vertex has two scribbled edges touching it, right? That must be true because the Hamilton circuit has to arrive along one edge and then leave along a different edge. So that's the first thing that I'm going to write here. Each vertex has two scribbled edges meeting it. And I will just say parenthetically, 3 would be illegal, right? I'm hearing a strange noise. I don't know what that is. Someone with a tuba that can only play one note. All right, each vertex has two scribbled edges meeting it, and 3 would be illegal, right? If you had, if you can imagine, if you had a graph where, let's say, you ended up scribbling in 3 edges here, that would represent some kind of circuit which is revisiting that vertex, and that's not allowed. So in a legitimate Hamilton circuit, that is not allowed. Each vertex has only 2 scribbled edges meeting it. All right, and the other simple observation: there is no subcircuit. What I mean by subcircuit is like a smaller circuit as part of the larger one. A subcircuit would look something like if I had maybe this graph and some kind of a figure 8 pattern where you went around here, right? This big figure 8 is like one big circuit, but it has 2 smaller subcircuits. That's what I mean by subcircuit. It's like a smaller circuit which is contained inside of the larger circuit. That's not allowed in a Hamilton circuit because, again, this would require revisiting this vertex, which is not allowed in a Hamilton circuit. So there is no subcircuit. I will just say, if there was, it's illegal, right? For in a Hamilton circuit. If there were a subcircuit, that would mean that you must have revisited one of the vertices already, and that's not allowed in a Hamilton circuit. All right? So we're going to try to reason in terms just of these 2 simple properties. They seem very simple to me at least, but it turns out you can get really far by using those 2 properties and approaching every graph kind of like a little puzzle. So here's, I'm going to try an example. This would be like a typical homework problem. This is kind of an easy one, but we'll do harder ones also. Here's a graph, right? I still hear it. Here's a graph. I would like you to either draw a Hamilton circuit or explain why it does not exist. Now, you may already be able to just guess where the Hamilton circuit goes, and that's fine, but I want to try to actually reason it out with no guessing, just because in a much larger example, you're not going to be able to guess it. You want to actually have some kind of reasoning here. So how do we begin? The 2 rules, remember? Each vertex has 2 scribbled edges meeting it, and there will be no subcircuit. Check it out. I would like to look at this vertex right here, and in the Hamilton circuit, which I'm trying to build out of nothing, I already know that there must be 2 scribbled edges which hit this vertex, right? I think that means this edge and this edge have to be scribbled, okay? If there's going to be 2 scribbled edges meeting this vertex. So the first thing that you should do, how I would get started here, look for degree 2 vertices. Now they're yelling. Don't you know any other notes on your tuba? Look for degree 2 vertices, and both of those edges at a degree 2 must be part of the Hamilton circuit. So you can scribble those edges in. Look for degree 2 vertices. Scribble in those edges. Right? So those 2 must be part of the circuit, and also on the far side, those 2 must be part of the circuit. All right? That was using my first rule there about every vertex has to have 2 scribbled edges through it. So if you see any vertex which is degree 2, those two edges must be part of the Hamilton circuit. What about the other edges? I want to decide, can these other edges actually be part of the Hamilton circuit? I would say this one here, look at that edge right there. That edge cannot be part of the Hamilton circuit. Would anyone like to give me a reason why in terms of the two simple properties? Yeah?
Because there would be more than two edges touching the
I'm not sure of that. If you were to draw this in, which is not right, so don't do it. There's still only two scribbled edges touching each vertex. There's a different problem though with including that edge. Yeah. Yeah, this made a sub-circuit, and that's not allowed in a Hamilton. So you cannot use this edge. So I'm going to put like a little X there. And also for exactly the same reason over there too. All right, so these two edges, these are excluded because they make subcircuits. Right? You can't use those two edges because they would have made a subcircuit. Okay, how about the others then? Now, check it out. This is like a cute little puzzle. I hope you like cute little puzzles. What about, look at this vertex here, right? Now, it used to be a degree 3. I mean, it is a degree 3. But I have excluded this edge. That means I have to use this edge near this vertex right here. So I'm going to try to kind of zoom in on this little area right there. Sorry to scroll. What we have is that if you just zoom in on that vertex, where this edge I already know is part of the Hamilton circuit, this edge is definitely excluded. It means I must use this as the other part of the Hamilton circuit because this vertex must have two squiggly scribbled edges going through it. And so you have to use this one over here. All right? So I'm gonna try to sort of narrate why I'm making these choices that I'm making. But after excluding those, so those two got excluded. Sorry, I sort of wrote right over my words. But in any case, I'll try and do a little narration. Having excluded that one, having excluded this one, now we must use this one because every vertex needs two scribbled edges going through it. And that's the only other choice that I have there. So I must scribble this one on the original picture. All right. And by the same reasoning, if you look at this vertex right there, this one in this corner, by the same reasoning, I have excluded the edge coming straight down, which means I must use this edge going straight across. And that's it. Now actually I'm done, right? That is a Hamilton circuit. It uses every vertex once without repeating any. All right, so this is the way that you're going to construct Hamilton circuits. Start off by looking for the degree 2 vertices, and then it's a matter of sort of try to exclude some, and then based on those exclusions, because of subcircuits, you can decide that in that case, since I excluded this one, that means I have to use this one, and so on. This is the kind of reasoning that's used. It's sort of simple, but I don't know how simple it is. It's like solving a puzzle in steps. You say I have to use this one, that means I cannot use that one, and since I didn't use that one, then I have to use this one, that kind of stuff. All right, let's just try a couple more. How about this one, by the way? This one, I think you could just look at that example and say, oh yeah, you should just go around the outer edge, and that's a Hamilton circuit. So that one is an easy one just to guess right out of the box. But like I said, in general, we don't want to rely on guessing. Let's try this one. This is one of those examples from before where somebody was able to just guess the answer. You sort of go around the outside, but then you cut into the middle at one point, and then you go back around, finish doing the outside. But let's see if we can do, by the same reasoning as before, build the Hamilton circuit without any guessing, all right? Again, I begin by identifying degree 2 vertices and scribbling those edges in. And actually, in this example, that's almost good enough to to finish the whole thing. The degree 2 vertices are here, 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 right? And I scribble all those edges. Here, 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 like that. I think the tuba is done. Sounds like it to me. All right, those are all my edges. Now, I've scribbled in all the ones that I can. Now I'm going to start thinking about excluding some edges, right? In the previous example, I excluded ones because they would have made a subcircuit. So it's a good idea to look here and ask yourself, are there any edges here which at this point would make a subcircuit if I were to use them? But actually, I don't think I see any edge like that. If you were to include any of these edges, it would not make a subcircuit. But there are some edges in here that at this point would be illegal to include. Does anybody see any edge here which you definitely cannot use, given the ones that I've already scribbled in? Remember, the two rules were no subcircuit, and also you can only have two red edges meeting at any point. Are there any edges which are not allowed to be scribbled at this point?
The middle, like that middle line, the left side.
Yes, this one here I think she's referring to. You cannot use that one. It's because that would make 3 meet at this point, which is illegal. So we exclude this one. And I see one more for the same reason, the one on the bottom, this one also. All right, so these guys, these are excluded because they make 3 meet. Right here and here. All right, now that I've excluded those two, are there any more? Does that make much of a difference? Can I include or exclude? I think at this point, I actually don't see any more that I can for sure exclude or say for sure you definitely have to do it. I think actually there are 2 ways to finish this. So this will have to, sometimes when you're doing these examples, you'll have to do this. Try to reason out as much as possible, and then you may have to guess a few at the very end. So at this point, actually, there are 2 different solutions. You could, I'll try and do 2 different answers in 2 colors. You could finish like that, and that would be a Hamilton circuit, or you could finish like this. Either one of those 2 would be valid answers. So can I just say, oops. At this point, now we just guess to finish. Unfortunately, sometimes you're going to have to do that. And the 2 ways you could do it in this example is like this, and then you could go up here, down the diagonal. You could do that, or you could do, sorry, I'm doing great. Or you could do this way, which I think that's the way we did it before. Right. Do as much as you can without guessing, but then sometimes you may have to just make it up at the end. And here, you know, you had to guess because there were actually 2 separate correct answers, so you just have to choose one. All right. Any questions about that? Let's try another. What about, I want to make a very slight modification to that example where that extra diagonal edge goes the other way, that way, instead of, it used to go up and to the right, now I'm going down to the right. What happens this time? Again, we begin by scribbling in all the degree 2, all the edges which meet degree 2 vertices. Those are here, 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 and here. That's a symptom. My dad was a very loud sneezer. My wife is also, don't tell her I said this, my wife is a loud sneezer, but she does the pre-vocalized sneeze. It's like a And I say, like, you don't have to do the, yeah. It's not actually part of the sneeze. It's her own decision to do that. She chooses. It's a lifestyle choice. Anyway, in this example, scribbling in the degree 2 edges gets you this far. Now, how do we finish? Actually, in this case, you can't finish because what I've done already is a subcircuit, right? This is already a circuit, and I missed the vertex in the middle. So here, we can immediately say this has no Hamilton circuit because I was forced to take all of those red ones, but this forces a subcircuit, and so the whole thing must be impossible. This is no Hamilton circuit since we were forced into a subcircuit. So there is no Hamilton circuit in this one. All right, and exactly the same, can I just say, same for this example that we did at the very beginning, and I said it's not possible to find a Hamilton circuit here, but it's not so obvious how to say why. Actually, this is how you say why. If you do, that extra edge didn't matter. If you do exactly the same reasoning, taking the degree 2 vertices, you have to go around the outer edge, and this is a subcircuit because I didn't use the vertex in the middle, and so it's impossible. All right. We made a subcircuit. We were forced to make a subcircuit, and so this one is impossible. That's how you're going to end up showing that it's impossible. If you are forced to make a subcircuit, or sometimes you will be forced to make 3 scribbled edges meet at the same vertex. This would also mean that a Hamilton circuit is impossible. Let's just look at one like that. How about this is a big triangle like this with extra vertices inside the edges. All right. We start as before. Start off by finding any degree 2 vertices and scribble in all the edges around the degree 2 vertices. Like so, like so, like so. We are forced to use all of those, and then, like before, we can immediately stop and say this is impossible because we already have produced an illegal configuration, right? Because we have 3 red scribbles meeting at the top vertex. So here, we were forced to have 3 scribbled edges meeting, and that is illegal. This is illegal. So, no Hamilton circuit. All right. That's how we do it. Any questions about that? I got a couple more, and I got one for you to try. How about this is a big and complicated one. Make sure you draw the picture big enough. It's a pentagon inside a pentagon. And it's connected up like this with some extra vertices on some of the edges. All right. This one has a slightly more elaborate sequence of going through the reasonings. I need to include these edges. That means I'm going to have to exclude these edges. Then I'm going to include these, and so on. That's how you need to think these through. Anyway, you should begin by copying the picture down. But then identify any degree 2 vertices and make sure you use all edges that go through degree 2 vertices. In this picture, the degree 2 vertices are just the dots that you see there, right? They are here and here and here and here. I believe everything else is degree 3. So I'm going to scribble in those edges. here, and here, and here, and here. All right? Okay. This is how we start. Now at this point, you want to think about, are there any edges here which I can exclude? That would be either because they would make a subcircuit or because they would make three red edges join meeting at the same point. Does anybody see any edges here that you can exclude for one of those reasons?
The straight one, the vertical one?
Yeah, this edge right here, right at the top, the vertical edge there. This one is not allowed. Why not?
Because it'll make, that's a degree 3.
Yeah, because that would make three scribbled edges meet at the top, and that's not allowed. So we exclude that edge right there. I will just say, as my little commentary, this makes 3, right? We don't want 3 scribbled edges meeting at the same point. Okay, having excluded that edge, does this make you able to scribble in any more? I think it would be natural to look just, okay, I excluded this edge. That's because of what happens over here. Does that affect the situation down here on the other side of that edge? I think actually it does now. This vertex, there are now only 2 remaining legal edges here. And so we must use those 2, right? Because every vertex, you need to use 2 edges at every vertex. And at this vertex here, there are only 2 to use, and so we gotta use those 2. So that forces us to use those 2 edges, right? Okay. Given that I've used those 2 edges, now can I exclude any more? Either because they make a subcircuit or because I have 3 red edges meeting at a single point. Does anybody see another edge that I can exclude at this point? This is like a cute little puzzle, if you like that kind of thing. Anybody like cute little puzzles? I know one of you does. What do you think? I'm looking for an edge which would make a subcircuit. I would like to exclude that. Or an edge which would make 3 meet at the same point. We also need to exclude those. What do you think?
I did it a different way. Is there a different way to do it that would work, or am I wrong?
Maybe. I don't know. Did you just guess a bunch of edges at this point?
No, I didn't guess them. Like, I just counted to see, like, when 3 wouldn't meet up. Like, I excluded the lower left one, and then the lower right.
This one here?
Yeah, I excluded those 2.
And this one?
No, on the other side, the opposite side.
Oh, this one.
Yeah.
I think actually you need to use those.
I didn't put the lines at the
Oh,
top.
you
Yeah,
didn't use
yeah.
those?
Yeah, I used those, but then below it, those 2 connected to the others.
These 2.
I didn't use those.
I think you have to.
Oh, okay.
Yeah, you have to use these 2 because you're not allowed to use that one, and in order to get to this vertex, maybe your thing doesn't go through that vertex. I'm looking for one more edge which would make a subcircuit or make 3 of the red edges meet. Anybody else see one? Yeah?
Bottom of the middle pentagram.
This thing. Yeah. If you did include this, it would make a subcircuit. It would make this small pentagon into a subcircuit. So that is not allowed. Thank you. I exclude this. That's because this one makes a subcircuit. And so we cannot use it. Right? And then how does that change things? Having excluded this one, I look at these 2 vertices. The one on the left, actually, I have only one other way out of there. I have to use this edge, right? Because you have to use 2 edges at every vertex. And I've already excluded one of them. So that means we must use this one. And similarly, we must use that one. We are forced into using those 2. Right? And we just proceed in every step. You are always thinking about, are there edges which I can exclude because they would make subcircuits? or because they would make three red edges meeting. Anybody see any that we can exclude at this point? I see someone give me the signal. Someone's doing this. Yeah, I think this last horizontal one, this would also make a subcircuit now. This sort of weird keyhole shaped thing would make a subcircuit. So the one across the bottom there also is being excluded because that would make a subcircuit. And that means at these two vertices, here and here, this one, the red stuff is gonna have to go up there because there has to be two of these edges that are gonna get scribbled in. And this one is being excluded, so it's gotta be that one. So here, and similarly on the other side, you gotta use this one here. And that's it. This is the Hamilton circuit. It's using every vertex, right? It had to be that way. I think actually there is not another way to solve this problem. I don't think it's possible to do it in any other configuration. All right? We got 5 minutes remaining. Can you guys try one? Maybe we'll just do it all together. Let's try something like this. With some extra points marked. All right. How about that? Either find a Hamilton circuit or explain why it's impossible. So we're going to either try to make these particular moves until it builds a circuit, or until we are forced to either make a subcircuit or make a three meeting at the same point, in which case we'll say it's impossible if that is forced. As usual, start by scribbling in the degree 2's, the edges which meet degree 2 vertices. And there's kind of a lot of degree 2's here. There's these ones, and then also the ones in the corners, right? So I'm going to begin by scribbling in all edges which meet those degree 2's. That's this, also across here, and across here. And also those 2's on the four corners of the rectangle. That means I'm gonna have to scribble in here, and also here, and also here, and also here. All right? All of those edges must be used because of the degree 2's. Yeah?
What about, because then the two vertices like on the middle on both sides, like they'll be like degree 3.
Yeah. If you look here and also here, we now have 3 of the scribbly edges meeting. That's not allowed, and so that means this graph is impossible to do a Hamilton circuit. So this has no Hamilton circuit because we were forced into this illegal situation. Circuit. It's because we have 3 edges meeting, and that's not allowed in a Hamilton circuit. All right?